So hey robot makers, do you want to know how to create your own Raspberry Pi cluster, or clustered Pi as I call it, and design an enclosure using Fusion 360? Then this is the show for you. So let's dive straight in. My name's Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Okay, so yes, today we're going to be looking at how to build this cluster using Fusion 360 as the physical design of this, designing all the different components for it. We're going to be looking at what a cluster is, from the cluster technologies, things including Docker and Kubernetes, and also looking at Fusion 360 design and progress. Yes, Richard, a bit of deja vu there. For people watching this back on YouTube, they won't know what we're talking about, so you need to join these live if you want to get on some of the jokes. Okay, so yes, we're going to be setting up a cluster. You can see a little picture of what it looks like there, and I also have it on my overhead camera here. This is my prototype that I'm building as we speak. Let's get back over to Keynote. So we're going to be looking at how clustering works. So that's part of what this project is about. So we're going to be learning together how we can cluster things. I want to also include some graphing dashboards. So I've got loads of data in Node-RED and in the home automation software that I use. I want to graph that with something called Grafana. So we're going to do a session on Grafana. We're going to take some data from the MQTT broker, which we'll also look at, and we're going to make it pretty pictures and graphs and charts with that. To store all that data, we need a database. So I need to set up a database and a secondary database server as a backup, and also the web server to host all the results on. So we need a couple of web servers just to fault tolerant and load balance. So we're going to be having two different web servers. One will be to host and build Jekyll sites. If you've not come across Jekyll before, it's what's used in GitHub pages in the background. I'm just going to turn my volume down a little bit more there. Hopefully that's not too bad. And then the other one is for hosting Python Flask projects. So Python Flask projects allow you to sort of create dynamic websites in Python. So they're two of the web servers that I want to build. And then we're going to be looking again at home automation with Node-RED. We've previously looked at that in a different video, but this time we're going to be hosting in our clustered environment. So I've got all these different bits and bobs of servers. I want to put them in one place and then build the infrastructure using code. And we'll look at how to do that in this series. And yes, clustered pie rhymes with custard pie. I always like a good pun on these things. Okay, so Fusion 360 design. So this design is going to host up to 12 Raspberry Pi Zeros. I'm going for the Zero with the Wi-Fi, so that's the Zero W or the Zero W2, which has come out recently. The panels that are on the design, the holder, they're going to be removable, so we can get access to the pins, the memory cards, and so on. So they're kind of optional, but they make it look quite attractive when it's sat there on your shelf or wherever this thing's going to live. And we want to design the parts as basically a single part that we can then rotate around. So we only have to design the part once, and we know that it will fit together. And we can just print 12 of them to create the full model. And currently no screws are required, so you can just fit everything together and it'll all click into place. Okay, so design inspiration. So I was quite fascinated by this as a child. In the mid-1970s and then early 80s, there was these computers, these Cray supercomputers, and I think the BBC, British Broadcasting Corporation, they had two of them for forecasting weather. And these things were the most powerful computers on the planet at the time. I think the Pentagon had about 5 of them. Very, very expensive. They were about $33 million at the time, equivalent money today. So very, very, very expensive. But just check out the specs below. So both the Cray-1 supercomputer and our humble Raspberry Pi Zero 2 are both 64 bits. The processor speed of the Cray-1 was 80 megahertz, whereas our Zero 2 is 1 gigahertz. So it's an order of magnitude, 2 orders of magnitude quicker than that. The memory, the Cray had 8 megs of memory, which again is quite pitiful compared to today's. People were complaining that the Raspberry Pi 2 only having, Raspberry Pi Zero 2 only having 512 megs. Imagine if you only had 8 megs of memory. You wouldn't be able to do very much in that, so you have to write a lot of stuff to disk. And then floating point operations per second. So the Cray-1 had a blinding fast 160 mega, which is million, 160 million floating point operations per second. Whereas the humble Raspberry Pi Zero 2 can do 24 gigaflops. That's 24 million floating point operations per second. So an order of magnitude many times above that original Cray. And that's all in the GPU that's designed to do floating point operations. So yes, pretty hefty stuff. Now I saw one of these in person. That picture on the right of the slide there is one I took myself at the British Computer Museum, which is in or next to Bletchley Park, down in Milton Keynes. So I had the pleasure of actually seeing one of these things in person. Although it says on the sign, "Do not sit here," you're not allowed to actually sit on those little seats. But you can see there are all the different slots where you could put all the different circuit boards, and I think they were probably memory cells that were in there. And the idea is all the components are really close together, so all the wires that connect them up could be close together as well. And all the power supplies and other stuff were in those seating components underneath. So quite a large thing when you see it. It's about 2 meters high, probably about a metre and a half across, and it was in this sort of C configuration, which is very similar to what we've got on the desk there. So this was the inspiration when I was thinking about how could we design a Raspberry Pi Zero enclosure that looked a bit different. So that was the inspiration. So what is a cluster? We've talked about cluster a few times already in this video. What do we actually mean by that? So a cluster, this is according to Wikipedia, a cluster is a set of computers that work together so they can be viewed as a single system. Now, it does go on to specify some other things, and I actually would disagree with some of those other definitions of that, having built some clusters and worked with some newer clustering technology as well. So typically what we have a master controller, which is one node which will look after all the other nodes. So it will start, schedule the tasks, it will check all the node health and so on. And then we have a whole load of nodes that are usually the same kind of size, memory-wise or processor-wise, but they don't have to be. So each of the nodes, you have any number of nodes that are all managed by that master node. Now it might be that you have all these things collectively wired together so that there is one set of memory, there is one storage, storage disk or something, storage point that they all access, or they might all be completely separated and they just receive a task from the master and then they work on it individually and then send the results back. So that would be like a render farm if you were creating an animated movie and you wanted to sort of render each frame at a time. You could have each of the nodes rendering an individual frame, and therefore it's quicker than just doing it on a single machine. So some of the basic concepts and different types of clusters. So highly available clusters. So this is the type that I built when I used to work in a college many years ago. So we had 3 servers in that particular one, and the idea being that when a request comes in, it hits one of the servers and that server responds back. And if any one of those 3 servers went down for any reason or you had to do some maintenance, it was still available. People could still get access to the resources that they needed from that, and it would continue working. So highly available is just about having a number of nodes, balancing the work across them so that if any one of them goes down, it doesn't bring the whole system down. High performance, you'll hear the term symmetric multiprocessing systems. That's what that Cray was. However, most common computers, in fact, the new Raspberry Pi Zero 2, I was just looking around to see if I had one there, that has got more than one core in it, and all the cores share the same memory, so that is symmetric multiprocessing. That's SMP, as you might see on some of the specs. So they all share the same RAM, but they have their own cores that they can execute code on. And you have to be careful when you're creating code for SMP systems, because what happens if you both write to the same piece of memory at the same time, you'll get some corruption occurring. So you have to have locking things in place to make sure when you're parallel processing that you don't accidentally write or read from the same address at the same. Reading's not so bad, but writing too, you get all kinds of collisions, they call them. So you need to have some kind of lock. And even creating a locking mechanism is quite complicated. So usually built into the actual hardware, there is some kind of set and test. So you can see, can I set a bit and then can I test, is that bit set? And then can I unset it? Is transactional, so you can either do it or not. It's like an atomic transaction. So that's high performance systems. Disaster recovery, so work and tasks can be routed to a healthy node in the event of a disaster. So say you've got 4 nodes and one of them goes down, whatever was working on that one, the master node will know what was working on that, and it could just restart that work on another node as if nothing had ever happened. So it's similar to a high availability, but it can recover from that by detecting which nodes are healthy and which ones are not, and recovering from that. A clustered file system is where you've got many servers that share the same file system. Again, when I worked for a police authority. They had several servers that all used the same SAN, and they would connect to that by fiber optic cables, and each of the servers would have a cable going back to the server from the storage array. So they were sharing the same disks, the same arrays, and it was presented to them as just like a single file system. So there is different options nowadays for doing that across the internet. You've got things like Gluster, which is like the Google file system, which is often used to sort of pull together lots of separate disks and present them as one high-level file system. So that's what we can use for that. You can use just file sharing, just SMB, which is quite common on Macs and PCs, Windows file sharing. Or if you're in the Unix world, they have like, is it NFC? Is that right? Which is the file sharing protocol for Unix systems. I don't think it's what is it actually called. Let me just go and have a quick look on the old file browser there. NFP, that's what it's called, Network File Protocol. Then we have heartbeat monitoring systems. So the idea here is that we have the master node, and it's checking to see are all the other nodes healthy. And the way that it does that, it has a separate local area network, so different Ethernet cables going back through a separate switch that are just connected to this heartbeat monitoring. And the heartbeat monitoring system essentially just sends out a ping to that node, and the ping says, yep, I'm still alive and everything's good. So that heartbeat might be sent, say, every second. If one of the nodes doesn't respond to that heartbeat request, then the master node can say, there's clearly a problem, let's bring down that node, and then, you know, alert an operator to go and kick it or do whatever they need to do with it. So that's what that's about. What else have we got? I was just thinking there about back in the day when people used to have these big tape-to-tape reel or physical hard drives that were, you know, they had pieces of concrete in them to try and steady them. They were like the size of washing machines and just as heavy. And if that disk had a problem, it was spinning round and then it would suddenly stop. The whole thing could fall over. And that's where that term, the computer's fallen over, or it's fallen over, it's gone down. Sometimes that would physically happen. These things would just clunk and fall over. So that's heartbeat monitoring. So yeah, usually a separate LAN connection. We're going to be using a poor man's version of this, so it's probably just all over Wi-Fi, because that's included in the Raspberry Pi Zero. We don't need to buy any extra add-ons for that, but if we bought extra dongles, that would bring the price up a little bit. And then the render farm. So I talked about that earlier. If you've got a computer-generated imagery, animation, and you want to render lots of different images to build up a movie, then it's easier if you've got lots of different machines to do that on, so you can spread that across. So I built a Blender render farm. What was the guy's name who did that? Was it Kent? He was on Blender Cookie. If you go to blendercookie.com, he had a really good tutorial about how to build your own render farm using Blender, and that has all the different technology for receiving. It essentially has a master node and lots of worker nodes, and it will figure out all those different tasks for you when you click the render button, and then bring them all back together at the end as a movie. So that's some of the terminology that we've got there. So we've talked about Docker at the very beginning as being a clustering technology. So what is Docker? We did look at Docker in the ROS video. So when I edit this, I will put a link to the card up there, wherever the right way is. So it's that way in the corner. So Alex, just make a note about the ROS video, and I'll make sure I put a link to that. ROS. So yes, Docker is all about software containers, containerization. So one of the challenges that software developers often have before we use containerization is they would develop a piece of software and it might use some libraries. So say you're developing a Python application and you're using the OpenCV library. What might happen is OpenCV might release a patch to that version, or they might have a completely new version, and that gets released. And if somebody who's managing that computer upgrades that library, it might break your code because there might be a function that previously worked that no longer works. And those kinds of dependencies, you scale that out to many applications that somebody's managing in an organization, that can be like hell to manage because things start breaking and we don't know why. So what are the interdependencies between all these things? So a container is a bit like a shipping container. It's a box that we can put our application that we built, we can put in there the libraries themselves so that we lock in that container everything that we need. So it's a self-contained unit, it will run the code, and it doesn't matter whatever version of libraries you've got outside of that, whatever is in that container we know is tested and works. So it can help when you're developing software, when you're shipping that to different servers, different organizations. Again, I've seen that where we have software developers with different libraries on their personal machines and the different libraries on the operational live machine. So they might be working on a cutting edge version that's not released or a really old version, and the live version is different. So that helps get rid of all that. We ship in the container everything that's needed for that application to run. So Docker enables you to separate your applications from your infrastructure and deliver that software quickly. Docker also enables you to manage your infrastructure in the same way. So you can say, I want to deploy this image to 10 different servers, and they can all grab that image, install and run just from a couple of commands on the command line. And this takes advantage of Docker's methodology for shipping, testing, deploying code quickly, and can significantly reduce delay between writing and running the code in production. So you'll hear that term in software development about continuous integration, and Docker helps with that because you can build a new container, ship that out, and then at some point just switch those over and the user might not even notice any difference. So that's what Docker's all about. It's about building self-contained packages that have everything in there to run a particular application. So many common applications such as, say, Ghost for creating blogs, or Node-RED, or anything that you can probably think of, Apache, Nginx, Redis, lots of different things can be simply downloaded and run with just one or two commands in Docker. So containers are very different than virtual machines. Some people might think, why not just use a virtual machine for each application instead? So it's to do with how lightweight containers are compared to virtual machines. So we can see there, they both sat on infrastructure. Containers use a host operating system and then Docker to manage all the different containers, all the different applications. Whereas a virtual machine, the one in red there, has infrastructure, it has a hypervisor, which is usually built into the operating system at a very low level. And then you have a virtual machine that replicates the entirety of the machine, including the guest operating system, the application itself, and anything else that needs to be in there, any of the libraries. And you can have several of them running at the same time, but managing an operating system on several operating systems in a virtual environment, that's quite heavyweight. You need a bit more RAM for that. Docker doesn't need that. It pares it right back down to just the applications and the libraries. So it's more akin to, if you're using Linux, to like a chroot, is it called? Or a jail on BSD, which is like a special environment that replicates everything. It basically just links to the host operating system rather than having to emulate it in its entirety. Okay, so containers are an abstraction layer. They help the package code and dependencies stay together, like we said before. Multiple containers can run on the same machine and share the operating system, kernel, and other containers if they need to, but each is isolated in their own user space. So if one of them crashes, it doesn't affect anything else. And they take up a lot less space than virtual machines. So typically, they're in tens of megabytes containers. They're really, really small, and they can handle, and you can therefore handle a lot more applications and require few virtual machines and operating systems. So you don't need any extra OS licenses either for this. So virtual machines, by comparison, they are an abstraction of physical hardware. So turning one server into many servers, and the hypervisor allows multiple virtual machines to run on a single server. So as long as they're the same architecture, that's fine. So you can't take a virtual machine that's designed to run on an Intel 86 processor and run that on, say, an Apple Silicon chip. That doesn't work. So it has to be the same architecture for that to work. And then each virtual machine has a full copy of the operating system, the application, the binaries, the libraries, taking up to tens of gigabytes, and they can be slow to boot, whereas Docker is like really quick. Okay, so that's the differences between the two. So what is a container then? So we talked about it being it's a sandbox process on your machine that isolates all the other processes from the host machine. So if that fails or that tries to do anything it shouldn't do, it doesn't matter, it's in a sandboxed environment. So a bit like when you're a kid and you're playing in the sandbox and everything was safe, nothing can go wrong in there. I always think about sandboxes outside and cats, use them as litter trays, so I'm not sure that analogy is great there. You shouldn't find any surprises in your sandbox. So the isolation leverages kernel namespaces and C groups, features that have been in Linux for a long time, and Docker has worked these into capabilities to make it very easy to use. So it is very easy to use on a command line. They've now got a Docker desktop tool, which I think is available for Mac, Linux and Windows. I'm not sure about the Linux part, definitely for Mac and Windows, and it just means you can see them visually, so that's very easy to use. So the architecture, bits and bobs, this is again how Docker works. So we've got the idea of a client, so we've got a command line, or we've got the remote API or the dashboard tool. That's the thing that we can use to sort of create or manage or destroy our containers. We have the host itself, so that's the machine that this is running on, so that can have many different containers. It's got a daemon at the top, the service that's running on our machine, and then we've got all the different images. So an image is just a container file, the flat file that contains the libraries, the application itself, and all the config. That's what an image is, and we can store them in a repository, in a registry. So a registry just has all those different images in there. And registries can either be public or private. So you might have a private one for your company, or you might use the docker.com registry for a lot of the common images that are out there. So you can download, for example, an entire image of Ubuntu and have that installed on your Mac just by using Docker. You can do the same on a Raspberry Pi as well. So just a reminder, if you like these videos, you want to make more of these, give this a like, a comment, or subscribe, or subscribe to the channel. Or if you don't want to subscribe, you can just watch more of the videos as well. That can help out too. So yes, give this a like if you're watching on Facebook or watching on YouTube. If you're watching on Facebook, you might want to consider moving over to YouTube when these go live, because the interaction is a bit better. You get a kind of a richer experience than if you're just sat on Facebook. And yes, hit the notification bell as well if you want to get notified when new videos come out. I do go live every single Sunday at 7 o'clock Greenwich Mean Time. So we're not in the British summertime anymore, so ish doesn't apply now. It's definitely 7 o'clock GMT. Okay, so if you want to follow me on social media, I'm pretty much across all the different social things. I've not got a single account name that is on every platform. So on Twitter, I think I'm Kev's Mac. On Facebook, I'm Kev McAleer. On YouTube, you're already here. So that's Kevin McAleer 28. If you go to smarsfan.com, that's where I am on the World Wide Web. The mail, if you go to the link in bio, you can find a link to the join the list, and you can join our mailing list. And on Instagram, I think I'm Kevin McAleer 28. I think that's what it is. And you can see I post pictures almost every day on there of what I'm working on. Okay, so let's get back to it. So Kubernetes, what on earth is Kubernetes, aka K8? I was watching a really great video by Jeff Geerling about Kubernetes. He's done like a Kubernetes 101, and he talks about why K8s. Apparently, originally, this was based on some code that was written at Google, and Google, they're very into the Star Trek over there, and one of the characters on there is 7 of 9, the Borg, and the technology that Google uses to deploy its operating system images to all its machines, because it runs on basically desktop type type hardware. They use software called Borg because it's kind of like everything is the same, they're just units, very much like our clustering stuff. So they wanted to call their software something to do with 7. So that little spoke you can see on the side of the screen there, the logo for this, this has 7 spokes, and that's the reference to 7 of 9. Now, when the lawyers heard about this at Google, they were like, we can't do this, we will get sued, so let's call it 8 instead of 7, and hence K8 is why this is called Kubernetes 8. So what on earth is Kubernetes? It's got a very strange name. What does it do, and how does it differ from, say, Docker? So Kubernetes is a portable, extensible, open source platform for managing containerized workloads and services. So let's unpack that a minute, because there's quite a lot going on there. Portable means it can be used across lots of different platforms. So, Windows, Mac, PC, Linux, Raspberry Pis, whatever the architecture, it'll work. Extensible means we can add to it. It's very easy to add extra code to this or extensions. Open source means that you can download the source code and play with it yourself. And for managing containerized workloads and services, we've already looked at containers. We know what they are in Docker. This helps you deploy those containers to lots of different machines in a cluster. So that's what really this is about. It's about using an orchestration tool to send out the packages, the containers to all different machines that we have. And the other thing that it says there is it says it facilitates both declarative configuration and automation. So declarative configuration is where we have infrastructure as code. So we can simply type in a file, a YAML file that's called a playbook. We want to have, say, Nginx installed on 3 different computers, and here is the IP address of those 3 machines. So if one of those 3 machines gets wiped and you bring in a new one, all you need to do is just either change the IP address of that machine or add it to that playbook file, and immediately it will receive that configuration and it will be set up to run, and then we'll receive the container and then it will start running. So Kubernetes handles all of that stuff in a very, very simple way to manage. So playbooks and automation. So it has a rapid and large growing ecosystem. It's really becoming the flavor of the month. There used to be a technology called Docker Swarm, and the reason I pause there is it still exists, but it's now depreciated. So Docker had something very similar called Docker Swarm, but they're now downplaying any reference to that, and they're now saying use Kubernetes instead, it's better. So Kubernetes services, support and tools are widely available. So again, open source standard, it means we can use different company technology for this. So here's some of the concepts for this, and we'll get into this in future videos as well because it's quite a heavy topic. Easy to use, but heavy if you're not familiar with these things. So declarative config, so we can say to Kubernetes how many pods we want to run, and it will maintain that config. So if one dies, it will just spin up another one, and then that'll carry on running. We'll get to what a pod is in a second. Containers can be Docker containers. So Docker is a file format as well as a piece of software. So you can create images for Docker using other tools. As long as they're the same format, Kubernetes will take that and work with it. Workload, so a pod represents a set of containers on your cluster. So a pod is another layer of abstraction. So you can say, here's a container that's got my Nginx in it. It also needs to have like a database server or something. And the pod will sort of wrap around that and say, this is a unit of work, of tasks. And I will run that pod on a node in the cluster. So that's what the workload management is about. Orchestration, I think it's a really nice term. I always think about the conductor sort of orchestrating all the separate instruments in an orchestra. So orchestration is about managing, starting, stopping and monitoring of the pods, making sure that they're running as they should do. And if there's any pods that are misbehaving, it can shut them down and fire up a new one, or just alert the operator that that machine is now dead. It can help with storage, so it can manage storage volumes. We can snapshot those volumes. We can take in a sense an immediate instant backup of that, just like you do with disks nowadays. Is that snapshotting spelled right? Shotting. And then configuration. So it has this thing called a config map. So if one of the challenges that you have if you don't use something like Kubernetes is, say you've got 4 nodes in your cluster and you have an IP address and the first one ends in 1 and then 2 and then 3 and then 4. If your application requires that it runs on a specific IP address, it gets really fiddly then if that isn't running on the IP address server that you expect it to. So say this is hard-coded to run on server number 1, and then for whatever reason server 1 dies and it's running on server 2, you'd actually have to open up the configuration file, change it, recompile the code or whatever, send that out to that package out again, and then have it run. You don't need to do that with config map. It will essentially say these are all the things that this needs to run from an IP resource point of view, and it will map them so that it's kind of variable and you don't have to worry about that. So for example, I have a home automation system and I've got some hard-coded devices such as my bathroom fan and the bathroom heated mirror, and they have a SON-off, one of those software on-off devices, which can run MicroPython, so mains in, mains out. There's a little Wi-Fi chip in there. And they got some code written in C++, I think it is, through the Arduino. And they look to a particular MQTT server to sort of say, do I need to switch on or switch off? So they receive their state from that MQTT server. But the MQTT server is hard-coded into that device, so it's not very easy for me to change that. So if I now move to Kubernetes, I can manage all those kinds of dependencies without too much hassle. So that's what that's about. We'll get into that on a demo and a future thing. However, we don't have to use Kubernetes. We could just use Ansible. So in Jeff Geerling's video about the building your own Raspberry Pi cluster, he uses Ansible to do all the automation. And Ansible is another declarative configuration tool. So you can say, I've got 4 servers and they need to be running these applications, and it will send them out. The difference is that that will send it out to that machine and not to like a container on that machine. So it will affect that machine's configuration. But Ansible is very, very reliable. It's got a long pedigree and has been running for quite a while. So Fusion 360 design, we'll take a look at that, and then we'll get on to the Mailbag, and we'll also look at next steps. So we'll dip out into Fusion 360 and then come back to this. So I've got Fusion 360 running on my machine here. If I click over to here, I've got 2 files open. So the first one is, let me just grab hold of this here. So this is a little plastic piece, and the idea is that your Raspberry Pi will sit inside this piece. It'll push into place. So there's a little tab underneath, which is what this piece here is. So the Raspberry Pi can sort of sit in there as a sort of tray. And it's designed to be quite a snug fit so that this thing it's not supposed to fall out. They're not quite there yet. I need to adjust the tolerances on these ones. So I think this is an earlier iteration. It hasn't got the holes in the top like that one there has. So the idea is the Raspberry Pi Zero sits in there, and then there's just a little area next to it where we can put wires and things like that. So it's got some little feet in there as well. So the idea of the feet is that they can push into one of the base pieces. So I've got a base piece here, which is like a little slice of pie, and it's got 2 holes in it. And the idea is that we can get our piece and we can sort of push that into the 2 holes. Again, I think this was an earlier iteration where the tolerances were a bit better, but you get the idea. It sort of pushes into place like that. And then we just need 12 of them, essentially. So Richard's asking about do you think they were mini doors? What's that?
It's because of the weird boxes around.
Oh, right. Yes. Yeah, I thought that was something about this. So that's the clustered Pi holder, and we can quickly have a see how we've created that. So if I just drag this back to the beginning, and I just switch on the sketches so we can see that. We can see there I've started with a sketch. So I had in mind this is what this was going to be, and you can just see that little foot just extends slightly below the base of that to allow for the I don't know if you can see that the foot kind of extends ever so slightly past the bottom there of this piece. Okay, so then I just extrude that out by, I think it's 3 millimeters in totality. Got my calipers there to check things like that. I then created the feet, so the feet sort of come out the bottom there. That's a little sketch for that. And I've labelled my sketches as well, so feet and base. I then do another sketch which is for the tab, which is the bit that the Zero will sit on, and then I extrude that out as well. And then wanted to add a bit of fillets to this. So the fillets just give it a roundness. So I think if I move this to the right and then to the front, let's zoom in a little bit. And if I just turn off the sketch for a second, you can see there that fillets now made that nice and round. And then what I then do is I wanted a tab at the top and a tab at the bottom. So rather than redesign this, I've essentially just created a plane between the two. So if I just turn on my construction there, you can do a midpoint plane using the construct tool. You can go to this and you can say create a mid plane, and then you just specify one plane and another plane, and it'll create this new plane between the two. And then I mirror the feature, which is that tab, using that as the mirror. So we can see we've got 2 tabs now based on that same one. So any adjustments I make to the first one will get mirrored to the second one. And then what I've done, this is what I was talking about, the tolerances. There's 3 different faces that I change to adjust the tolerances, just to give it a little bit more breathing room. So when you 3D print, sometimes it's a little bit out, so you need a bit more tolerance there to make it fit nicely. I've then rounded off underneath here to make those just a little bit stronger. Whenever you've got like a 90-degree angle, it creates a weakness in your 3D thing. So if you print like an arch, it makes it so much more stronger, because that's the weak point. Then we've got another seat tab. So on the top of this seat, we want to have a little tab, and the idea here is we have a seat cushion. So I've got these little trapezium shaped things, and they're going to have little cutouts either side, so that when this pushes on between the seats, and that'll make sense in a second, it just gives it something to hold against. So that's what these tabs are for. I tried a few different methods for this, and this is the version I've settled on. So on this previous version, if I just go full screen for a second, you can see on the top there, this has got, it's actually got 2 little hooks. One of them sticks out and one of them doesn't stick out. And the idea is that the seat could sort of sit on one, and then it could connect into the other one on the other side. So they're designed to be not symmetrical. So you can just about see that there. Let's just put that back in there. Okay, let's get back over to here. So that's what I've come up with. That works better. Next, we do some holes for the tabs. So I wanted to have a top piece. If I just go to this overhead one, you can see here there's a little trapezium piece on the top, and that's a little piece that just pushes in, and we can have that on each of the different segments just to give it kind of like a roof over the design. So what I've done there is I've created a little hole just above that tab. So if I just push on to the next one, you can see that hole now appears. And then I think the rest of it is just me tidying up some of the tolerances here and there. And yeah, that looks like that piece is finished. Okay, so what I like about this, if I make any changes to this and I click save, let's just click OK on that. So we're on version 20 now of this Pi holder. If I now go over to the cluster Pi, which is the full version of this, we can now see that we've got this linked component is out of date, and all these different clustered Pi holders, which there is 12, are all out of date. So I just click that once, it will pull in that new model that I created and update this model which is based upon it, and it works instantly like that. So let's have a quick rewind of what's going on here. So let's have a look. So the first thing I've done is I brought in that clustered Pi holder. I've then moved the position of it because of that origin point there. I wanted it to be rotated around the origin point. And then what I then do next is I replicate that round. So I use the pattern tool. And what's really cool about this pattern tool is you can actually have it so that it creates, 16 of them in a circle, like so, but we can suppress certain ones. So the Cray-1 Supercomputer, which this is based on, isn't an entire circle, it's a C shape. So that's what I've done, I've suppressed a few of them, so there's actually 12 units, not 16. So that's a nice feature of Fusion there. So I've then created this bottom section. I've then just done a sketch for the bottom section and extruded that out to be a single piece. In this model I've used red as the colour because I thought that's kind of the Raspberry Pi, the Raspberry Red, whereas when I printed this out I just had some yellow, so that's the colour that's being for the prototype. But we can see there that the feet do indeed go inside this piece. So when I'm selecting that, you can see the feet kind of go just inside the bottom there. You can also see on the timeline on the browser all the different clustered Pi holders. You can actually turn these off if you want to, one at a time, if you want to make your machine a little bit quicker. Let's just bring those all back in. Okay, so next up we then replicate round using that circular patterning tool so that we've got 12 of them. So this is now starting to come to life. It's now looking like our Cray computer a little bit, like a skeleton version. I then bring in a Raspberry Pi Zero. I then just change the position of it so it's just off to the side there. And then what I do next, I'm just going to move my window a little bit so it's got a bit more real estate. I then do a join, so there's a rigid join onto the first one. I think I tried 2 of these, so I replicated another Raspberry Pi Zero, put that onto the second one, and then I thought, actually, I don't need to do this. I can use the circular tool once again to bring in 12. So there we go. We've now got 12 Raspberry Pi Zeros all up the header there. I wanted to make sure if we had header pins that they wouldn't clash. But we can see there that's working fine, and we can also see that the power and the video are all pointing towards the middle, so all our cables can come to the middle point. I thought that was probably the best way. If you rotated this round, the power and the USB will be at the top. Ideally, it should be at the bottom there. That'd be really nice, because then the cables could go in this sort of alcove section at the bottom where the seat is. So maybe in a later version I might swap it around to that. Let's just see when we get to the part where we're trying to wire this thing up. We could actually wire connecting the 5 volt and the ground to another power supply, but it has to be quite beefy because each of these can be like 2 amps each, and that's quite a lot of power if we're having all 12 of them powered up. So next up, I've just designed there the seat cushion, and we can see there that we've now got that seat cushion being brought in. At the moment it's clashing with the tab because I've not excluded the two of them, I've not combined them together. And then I've just created some fillets on there because this came in as a, if I just go back one, you can see it's quite angular there. So it's got very hard edges, and these two fillets just make it look a bit more like a cushion. So it's got some roundedness on all the different faces there. Then I do that combine where I actually cut away. So if I just double click that, you can see I've got an operation which is cut. I'm using that as the cutting tool, and I'm using that as the body that's being cut into. And I keep both parts, and that means now that if we hide those Pi holders, we can see that the cutout doesn't look like it is actually cutting out, does it? I shall probably have to look into that. But yeah, it should be cutting out that piece now, so that cushion has 2 sections either side. If that isn't the case, I'll have to fix that. Okay, so then next up is the front cushion. So let's just bring that in. Just going to fast forward to these. Yep, so that's the front piece that's being built there, and then we get to the part where that gets extruded out. So we've now got a front cushion, which is kind of the back of the seat. I think again I do the fillets of that just to make it a bit more cushion-like, so it's got some nice roundedness to it. And the idea is that that can sit there, and then it actually sits in, there's like a slot that it connects into, so there's a bit that pokes out and it connects into that. So if I just hide the cushion, you can see in a second I will add a new sketch. Let's just go to that one there and extrude out a little pointer. So if I do that now, we can see there's like a little tab just there. I might need to make that wider. What I've found is if it's like a millimetre, when you 3D print them, they are very small, and the hole that fits into has to be very accurate, and 3D printers are not great at printing things so small so accurately with the tolerances. So I found just printing these things a bit bigger, a bit larger, wider and more depth makes that a bit easier. So I then replicate round the cushions. So there's the cushion, they're all going round now, so this is really now coming into the shape we're expecting it to see. And then I think I do the same as well once I've combined those two together, again just to cut out that little notch. We then replicate round all the different seat pieces, and then finally we then start working on this top panel here, which is just here. And if I just fast forward that a little bit, so there's a little knockout hole. If I remove the holders for a second, you might be able to see. There we go. So there's a hole there, and there's a tab that goes into that hole, and the idea is they just click into place. So they're a friction fit, so there's no tolerances on them. And that does work. I've got one on the overhead. You can just see there that white one has that piece there. And then there's the cushions. They're currently just resting on there. I've not printed out the new version of each of these Pi holders, so currently they're just very carefully just resting on there. But yeah, they've not got that friction fit yet. So this is just an early iteration. So I do find this when you're designing things, sometimes you've got to work on several iterations. I think this is version 15 of the clustered Pi, and we're on version 21 of the Pi holder at the moment, so you can see how many iterations we have to go through for this. Okay, so then we mirror that tab so it's on both sides, because I think it starts on just one side. Again, if we hide some of them, we can probably see that. So we've just built that tab just there. So if I then do that one, you can see that tab appears there. I then mirror that around the center point of this thing, and we can now see that the tab appears on the other side too, so it's got a tab on both sides. And then I just do a circular pattern so that we have 12 of them going round. Let's bring our Pi holders back in, and we can now see pretty much the finished article. So if I just move that to the very end, I think that is it. So we can see there. So one of the challenges I had when I designed this model doesn't have a memory card in it. So when you put a memory card in, it does actually extend into this at this point. So I've got two options there. I can either, if I pull out this piece here, let me just destroy my model for a second. So if I just put the camera on this one for a second, we have a look at it. So we can see there's the tab at the top, which is holding in, but there's the memory card, and there's the tab hole we can just about see there. That's very close. So I can either extend this up a bit more, just to make that so that there's a bit of room for the memory card to exist, or I could just make it so you just take this out. Another option is to have one of these on every other one, and only have 6 Raspberry Pis instead of 12 in the cluster, but that seems a bit of a cop-out to me. So that's what we have there. Let me just put this piece back into place. And that's the design. So what I've then done, for each of these different pieces, I've gone into it and into the body. So Pi holder, I then save that as a mesh, and we can save that out as a 3D printable file. So I've got a couple of files. If I open up, let me just go to my machine for a second, and I shall show you the files that exist for this at the moment. So let me find, there we go. So going to shows, going to clustered Pi. Okay, and let me just share my screen. So we have the bottom section, which is just that bottom piece. We have the Pi holder. So this was version 19, we're on 21 already now. And we have the cushion, and we have the side cushion, and we have the top panel. So we just need 12 of each of them to create the full model. And then to power it, and what I'm thinking is, again, watching Jeff Geerling's video, he had a USB power supply that had a number of USB connectors on it to power the Pis, and it was just one device. So instead of having to have 12 of these and 12 bricks all in a big power supply, you could just buy one with so many wires coming out. We could do that. We could use the pins instead. Again, we'd have to make sure the pins have got the correct voltage and the ampage for the cable so we don't melt anything. And if we can get it so it's running through the middle of those seats rather than on the middle of the C, that would be so much better. Okay, and I'll come to some of the questions in a second and answer some of those questions. So I think that's everything I was going to cover off on the Raspberry Pi clustered Pi. So you can see there's my little prototype. You can get an idea of just how big this is. It's absolutely tiny. I just get a ruler out next to this thing. I mean, it's what, about 16 centimeters wide, something like that. It's not very big. And I have got a number of Raspberry Pis to go into this. Some of them are the original Raspberry Pi, some of them are Raspberry Pi 0, and some of them are the Raspberry Pi 2. I think I've got 3 Raspberry Pi 2s. So I've got a number of them to go into this model, but I might just get a whole set of Raspberry Pi 2s and just make this like a more modern one, just because it's got all that extra grunt in the CPUs, all those extra cores. Kubernetes might be a bit of a challenge just given the memory overhead that requires, and the Zeros don't have very much. So I might use Ansible instead. I'll look into that and come back with the results for that as we build that out. Okay, so let's just go back to the keynote for a second. There's one thing I wanted to cover off in my next step. So yes, so I'm going to print out the parts, I'm going to iterate the design, keep tweaking it until I'm happy with it, until the tolerances are all good. Make sure all the things interlock nice and tight and there's nothing wibbly wobbly about it and it's not too delicate. I'm going to assemble the pies, the zeros, I'm going to power them and network them. So again, if I go for the model that has Wi-Fi included on there, I don't need to add any extra cabling or anything. I'm then going to set up Docker on each of them using Ansible to sort of fire that out. And then I'm going to configure Docker images for Grafana, for Jekyll, which is the software we use for creating the web pages, Nginx to host the web pages, a database, probably MongoDB and MariaDB. One's a NoSQL and one's an SQL server, and then Mosquito, which is our MQTT broker. I'm then going to learn more about Kubernetes. I spent this afternoon looking at some videos about that. And then we can configure our cluster pi to use this if that's appropriate. And obviously make some more videos about this as well. So mailbag time. So I've got quite a few things to show you this week. So the first thing I wanted to sort of show off was I'm actually in this month's Raspberry Pi magazine. So this Make and Build with the Pi 02. You can see right on the first page there. So what page is that? 18. What page is that? Page 88. We have the Pico Tamachibi, which is our little Raspberry Pi Pico. If I just open this out, pull out the inside, you can see we've got a little Raspberry Pi Pico, and that's got a circuit board, and on there is a little screen and a couple of buttons, and that runs our virtual pet that we designed and did a video about. So I'll just put this back together. So I tweeted out about that. They have a Magpie Monday where they have a hashtag Magpie Monday, and if you tweet on that, sometimes they pick up on the pictures. I think if they're visually interesting, they usually pick up on them. So that was the first thing I wanted to sort of show you guys. The next one is the Mailbag. So I bought a few things I thought would be worth showing. So one of the challenges we have with our SMARS robot is powering this with 9-volt batteries gets quite expensive, so they might last a couple of hours and then you've got to throw it away. And they're also a pain to get at, so you've got to sort of slide all the Arduino stuff back, put the battery in, slide it back in. Now, when I was working with the Otto DIY dancing robot, which is just there, trying to get my hand to the right place, just there, that came with a 9-volt battery that was USB chargeable. So I bought a bunch of these. So these are 5,400 milliwatt hours. So they last quite a long time. It's 9 volts and it's rechargeable with the USB. So it even comes with a nice USB charging cable, so you can charge 4 of them at the same time. That means that we just need to iterate the SMARS design so that it has a little hole on the side, and I'm already working on that as well. So I've got a Fusion 360 file. If I just close this down, just wait a second while it does that, and then I just open up the SMARS model that I was working on. So there it is. I can just show you a very quick sneak preview of the design there. So if I go over to there and I just close this out, look, it's not even got any colour on there. Let's just throw in a nice colour. So A for appearance, and then let's just do like a yellow matte plastic. Let's just throw that on there. There we go. So you can see there what I'm working on is we'll put the battery in. Let's just throw you the 9-volt battery, and the charging port for that is just there. So we can just see the hole there. So that's what I'm thinking. We can have maybe a little plug or something you can fit in there when you're not using it, or maybe that's just part of the design. So I was just working on that as well this week. So I'm just going to close that down. The next thing I was going to show you is Pico LiPo. So Pi Moroni have produced their own version of the Raspberry Pi Pico that they call the Pico LiPo. So it's got the RP2040 chip just there, but it also has, if I just press the right button there, we should get the LED coming on. There we go, power. So that's now got the LED lit, and I've just got this connected to a LiPo battery. So the idea there is they've got a connector on the bottom. It's a Raspberry Pi Pico, but with a LiPo battery stuff, and you can just, it's got, even got USB-C there, so we can plug this in, charge this up, and charge the battery at the same time. So quite reasonably priced as well, these. This one also has the 16 meg of memory as well as the 4 that's built onto the Pi, so the Pico. So you get quite a bit of storage extra on this one as well. So what I'm intending to do is use this in one of the SMARS robots, which brings me on to the next bits and pieces that I bought. So I bought 2 things again from Pi Moroni, not sponsored yet, hint hint. And these are Kitronix motor shields for the Raspberry Pi Pico. So this one has got a Pico plugged in there, so you can see we've got a number of motor connectors on the side as well as the power in, and there's even a nice on-off switch as well, which is sadly missing on some of the other shields that we've got for the Arduino. And then I've got a much thinner version again for the Raspberry Pi Pico. Again, it's got the power in, it's got the on-off switch, and it also has the same power things there. So this is more akin to the Arduino size motor shield, and this is more akin to the sort of zero-sized form factor. Both of these fit very nicely in our SMARS robot. Let's grab our SMARS robot there. Oops. Let me just pull some of these bits out. So this is the SMARS that's got the wireless charging module plugged in, but the idea is we could just put a battery into there. We can sit this on top and connect that all up, and then we've got our SMARS robot Pico powered. So yeah, it'd be a bit smarter than that, but you get the idea. We could also use one of these as well if we wanted to, the 9-volt batteries, but I thought that was quite neat. I did also buy another bunch of Raspberry Pi power supplies, so I've got about 4 of them now on the go, and so they just look like this. They're a slightly more powerful version for the Raspberry Pi 02, but they do have the micro USB connector at the end, so it isn't USB-C. Don't know why they opted for that on there, but maybe it was just a cost thing again. I did also buy another bunch of Raspberry Pi Pico, so I've got another 5 of them. And they did some really nice headers for the Raspberry Pi 02. So let me just show you, let me find the right one. Here we go. So this is from Pi Hut, and this is a color-coded reference pin, GPIO pin. So the idea being that these are actually color-coded. So you can see there the red is the voltage, the black is the ground, the greens are just regular pins, and the yellow, not sure what the yellows are actually. But yeah, they're all colour-coded. Looking at my reference thing there to see if there's anything. I think it might be like a voltage reference, something like that. So these are much nicer to work with. I just grab a 0 that's not got any headers on, and I just plug that in. So there we go, that's what it will look like when it's sort of connected up. And you can see quickly that the headers are all colour-coded. So I think Liz Clark had some of them on her video, and I was like, that's neat, I need to get myself some of them. So they're like $1 each or something, they're not very expensive. The other thing was, where's it gone? There it is, Captain Reset. So this is from Pi Moroni, and it's called Captain Resetti, and it's an absolutely minute little button. I don't know if you can see that there, and you can put that over the pins, and it will just reset the Pico. So just give your Raspberry Pi Pico a reset button. I did buy a whole bunch of extra cables and odds and ends for the Raspberry Pi 02, so I've got so many of them. So that's like a USB converter cable. There's a HDMI, is it HDMI mini to HDMI, and there's also some header pins as well. So I bought a couple of them. And what was the other thing I was going to show you? I just saw that. Yes, so Adafruit, they do a Qt Pi, which is another Raspberry Pi Pico RP2040, but in a really small form factor. So I've not looked at this one yet. So this one's called a Qt Pi. There we go. That reminds me of that robot that Isaac Law has drawn. He's on our Facebook group, and he draws nice pictures of robots, and I think one of them is called Qt Pi. So yes, I think that's all the bits and bobs I was going to show you for the mailbag today. I think that's pretty much it. So lots of Raspberry Pi stuff. I'm sure there was another chip in there, but maybe not. Cool. Okay, so let's have a look at the comments. So this is the section of the show that when I'm recording this, I will cut off at this point. So if you want to see the comments, you need to watch this live. You need to be on the live stream. Otherwise, you'll be missing out on all this interactivity. So if you're watching on the YouTube video playback, I'll say bye for now, and I shall see you next time on a new video.